This is the 30th lecture, and the topic for today is BJT biasing and introduction to power amplifiers. We had discussed last time a BJT biasing circuit in which the emitter was connected directly to ground, the collector was connected through R sub C to plus VCC, a supply, and the base current was supplied by means of a resistance connected directly to V sub Cc, and this resistance we had decided to call R sub B. And we had seen that if due to any reason the current in the collector I sub C, if due to any reason I sub C increases, then the process is such that after several intermediate steps I sub C further increases, and this goes on in a circle till what you get is a thermal run away. It is as if the transistor cannot tolerate or accept any more heat, and therefore it runs away from its responsibility, which means that it gets damaged, it gets burnt out. Thermal run away. And the remedy for this that we had suggested last time and had terminated the class at that point was that you introduce to this circuit a couple of other resistances, namely you introduce a resistance from here to ground and another resistance at the emitter lead. This is the most common circuit that is used for biasing a transistor. This resistance which is connected to the emitter lead is called Re. The resistance that is connected from the base to ground is R1, and this resistance is redesignated as R2. And this is the standard terminology. I sub C is the collector current, I sub B is the base current, and the total circuit is called a self-bias circuit. Self-bias circuit. Let me draw this again and explain how this helps in getting the bias stabilized. You have a emitter resistance Re, a collector resistance R sub C, this goes to plus VCC, plus VCC because it is an NPN transistor. If it is PNP, then it would be the negative supply. Then you have a resistance R1 here, no R2, and the resistance from here to ground is R1. This is the circuit, and this current this current is I sub C, this current is I sub B, this current obviously by KCL is I sub C plus I sub B, all right, and the total circuit is known as the self-bias circuit. And to understand why and how the collector current stabilizes, you assume that due to some reason I sub C increases. If I sub C increases, then so does I sub C plus I sub B, and therefore the voltage drop across Re, if we call this V sub E increases. If V sub E increases, then naturally VBE shall decrease. VBE shall decrease, and if the diode voltage decreases, then you know the current shall also decrease, and therefore I sub C increase means VE increase, which means VBE decrease, VBE decrease, and VBE decrease means I sub B decreases, and I sub B decreases shall mean that the collector current, which is beta times, approximately beta times I sub B, shall decrease, and therefore the increasing tendency of I sub C shall be arrested, and therefore I sub C shall be stabilized. Qualitatively, this is the explanation of the bias stabilization due to the self-bias circuit. Quantitatively, in order to calculate the values of the resistances and what values of resistances should be put to get a proper operating point, the Q point as we call it, with stabilization of the operating point irrespective of changes of temperature, irrespective of replacement of transistor. This was the main cause, one of the main causes why the previous circuit could not be used, because that had kept IB constant, and therefore if we replace the transistor, the beta of the transistor, as you know, can have a spread of about 1:6, irrespective of whether the transistor is replaced, whether temperature increases or decreases, I sub c should remain a constant. Let us see analytically how this happens. In the process, you should remember, I will keep this circuit in the background, plus VCC, RE, R1, R2, RC, this is IC and this is IB, and this is IB plus IC. As many times as you draw it, the better. Now, to analyze this quantitatively, the transistor must be replaced by an equivalent circuit, and the transistor, simply the base to emitter, simply means that you require, the base to emitter is a junction, is a diode, and we assume that it is an ideal diode in series with a battery of VBE, which is approximately 0.7 volt for silicon and 0.3 volt for germanium, and therefore the transistor is equivalent to the following. It is equivalent to an ideal diode in series with VBE, all right. This is the base and this is the emitter, base emitter, this is the collector, and under this condition you know that if the base current is IB, then I sub C, the collector current, is simply beta IB plus beta plus 1 ICBO. The collector current obviously is independent of VCE, all right, and therefore the collector, at the collector simply there are two current sources. One of them is beta IB, and the other is beta plus 1 ICBO. Okay. This is the circuit, this is the equivalent circuit that we shall use for quantitative analysis. For quantitative analysis, we shall also use a simplification. You see, this branch consisting of R2 and R1 and VCC can be separated. That is, you can include another VCC here, it does not matter as far as analysis is concerned. So, at this R2 is connected to VCC, then connected to base and R1, and if we look to the left of this line, we can replace this by a Thevenin equivalent, and the Thevenin equivalent would be a battery VCC multiplied by Thevenin equivalent voltage source is the open circuit voltage multiplied by R1 divided by R1 plus R2. Is that clear? No. Well, let me draw it again. You have a VCC, then an R2 and an R1, and this goes to the base. We are looking to the left of these two lines, from base to whatever the point is, let us call it G. We are looking to the left of this line. So, what we have is, we have a battery VCC, then we have an R1 and we have an R2, and it is these 2 points that we are looking into for Thevenin equivalence, and therefore this is simply equivalent to a Thevenin voltage, let us call this VBB, in series with a resistance which is parallel combination of R1 and R2. We call this resistance as capital R subscript capital B. this is R1 parallel R2, and VBB obviously is VCC multiplied by R1 divided by R1 plus R2. Now this, as you will see, greatly simplifies the analysis. If we substitute this in the original circuit, then my equivalent circuit becomes, let me draw it on a separate sheet. The equivalent circuit becomes, I have a VBB, then I have R sub B, then the transistor RE, then R sub C plus VCC, and this current is I sub C, and this current is I sub B. Therefore, also this current is I sub C plus I sub B. Now if I write KVL equation around this loop, KVL equation, then I get VBB is equal to I sub B RB, the drop in RB, plus the drop from base to emitter, plus VBE, plus the drop across RE, which is I sub C plus I sub B RE. This is one equation in which the two currents I sub C and I sub B are unknown, but we know that I sub C and I sub B are connected by the relation I sub C equal to beta I sub B plus beta plus 1 I sub C B O, and therefore I can eliminate I sub B from here. Our purpose is to obtain I sub C and to see how stable the collector current is. So what I do is I replace in this equation, the first equation, I replace I sub B by I sub B equal to I sub C minus beta plus 1 I C B O divided by beta. Alright, I replace this here and also here. Then I can simplify the algebra and obtain an expression for the collector current I sub C. The result after this algebra, which I shall skip, is as follows. Let me write down the complete expression. The expression is I sub C equals to VBB minus VBE, and you can see where this comes from. VBB minus VBE, that means I take it to the left hand side, and then I shall have a term containing ICBO. ICBO comes from here and also from here. The term is beta plus 1 divided by beta ICBO, then RB plus RE. Write down the expression because it is a very significant expression, although a bit long, but we shall investigate, we shall go very deep into this expression to be able to understand how and why I sub C is stabilized. Why is it called a stabilized bias circuit? The denominator is RE plus RB plus RE divided by beta. This is the expression for I sub C, which contains its dependence on temperature through three things. What are these? In the denominator it is RE, there is no RC at all. This is correct, RE plus RB plus RE by beta. This is correct. Okay. Now, I want you to notice, I want you to qualitatively first understand how I sub C depends on 3 temperature dependent quantities. One is VBE. As you know, VBE decreases at the rate of 2.5 millivolt per degree C. This is VBE decreases at the rate of 2.5 millivolt per degree C, and therefore VBE is a temperature dependent quantity. Beta also increases with temperature almost linearly. Beta is proportional to temperature, all right, almost linearly, and I sub CBO increases, it doubles, it exponentially, it doubles for every 10 degrees centigrade rise of temperature. I sub CBO doubles for every 10 degrees C rise, which means that if I have, let us say, 2 temperatures T1 and T2, look at this modeling, very simple modeling. If I have 2 temperatures T1 and T2 where T2 is greater than T1, then I sub CBO2, that is at the increased temperature, shall be I sub CBO1, that is the decreased temperature, multiplied by 2 to the power T2 minus T1 divided by 10. Is that okay? This is a very interesting way of writing the expression. This is approximate, but we can work with this. Is this clear? That if T2 minus T1 is 10, then I sub CB1 is multiplied by a factor of 2, which is in keeping with this relationship, that is I sub CBO doubles for every 10 degrees centigrade rise in temperature, all right. It also can be affected, besides temperature, even if you keep it within a temperature stabilized enclosure, it can be affected by a replacement of transistor. A transistor goes bad in an amplifier, so you pull it out and put in another transistor of the same type, but you know beta has a large spread. It can vary by as large a ratio as 1:6. If the original transistor was a beta 30, the new one may have a beta of 180. But even then, you do not want I sub C to change. You want I sub C to be stabilized. And therefore, we must examine this expression as to how this stabilization occurs. Before I take up the question of stabilization, let me illustrate with an example as to how the things change with temperature, utilizing this expression. Suppose we have a transistor circuit. I will keep this expression in view. Is it visible? Okay. Right. Suppose we have a transistor circuit in which the beta, well, it's a silicon transistor, and beta varies between 30 and 180. As I said, 1:6. All right, a silicon transistor. VBE, the temperature is such that VBE varies between 0.5 millivolt and let's say 0.9 millivolt. It's a silicon transistor, but with temperature VBE can vary between 0.5 and 0.9. And I sub CBO can vary between, let's say, 1 nanoampere, nano is 10 to the minus 9, to let's say 10 nanoamperes, as much as 1:10. That means the temperature may rise, no, it will double for every 10 degrees centigrade, and therefore this is a large range of temperature. It is 2 to the power, what is the temperature difference for which the ratio can be 10? 10 is 2 to the 3 is 8, so it's slightly less than 4, 2 to the 4, yeah, between 8 and 16. Okay, what we want to know is what is the worst case variation in I sub C, all right. Obviously then you would want to know what the circuit is. Let's look at the circuit now. The circuit is the usual circuit, the self bias circuit. and let us say the values are given. The values are given as 10K, 90K, these are typical values, 90K, and then this is 2K, RE is 2K, RC is 15K, and VCC is plus 28 volt. This is a typical circuit, typical bias stabilized circuit. To evaluate the worst case currents, obviously you require the values of R sub B. R sub B is the parallel combination of 90 and 10K. If you recall, it's the parallel combination of R1 and R2. So it is 9K, and V sub BB, VBB is 28 multiplied by 10 divided by 100. So it is 2.8 volt. Is that okay? Now let us consider the worst case. We recall that I sub C is given by VBB minus VBE plus beta plus 1 divided by beta ICBO RB plus RE divided by RE plus RB plus RE divided by beta. The two worst cases are the following. One is that you put VBE, you want the minimum IC. You want the worst cases, that the minimum and the maximum. Obviously the minimum shall occur when VBE is 0.9, alright, because it subtracts. VBE is 0.9 millivolt, beta the smallest value, which is 30. Now you might ask me, why do you take the smallest value? Because this is 1 beta plus 1 divided by beta, and there is a division by beta here. Now smallest is 30, 31 divided by 30 and 181 divided by 180, they don't differ much, 1 plus 1 over beta, and therefore beta basically controls this quantity. So you put beta equal to 30, beta equal to 30, and ICBO put the lowest value, that will give you the lowest IC. Is that okay? Lowest value is 1 nanoamperes. You put down these values, then I sub C comes as 0.8 milliampere. Now the other extreme is when VBE is 0.5 millivolt. Let me indicate this in another color. The other extreme is 0.5 millivolt, beta is 180, and ICBO is 10 nanoamperes, beta is 180, and under these conditions if you put down the values, then IC calculates as 1.1 milliampere, and you see the range 0.8 to 1.1, approximately 30%. Is that okay? 30%. But this is not a very good design. It can be reduced to a much lower value by an appropriate design. But even a roughly designed circuit causes a change of only 30%. All right. Now after this demonstration of the example, let's look at this expression again carefully and see what should be our design steps. Obviously if you look at the dependence on beta, the numerator there is a term containing beta, in the denominator also there is a term containing beta, and as I said 1 plus 1 over beta, when beta changes from 30 to 180 doesn't make much of a difference, because 1 by 30 is 0.03 and 1 by 100 is 1.01, alright. So it doesn't make much of a difference. The dependence on beta, there are two reasons why it doesn't make much of a difference what beta is. That is because ICBO is also typically a very small quantity, and therefore the total quantity here compares negligibly with VBB minus VBE, and therefore beta dependence is mostly through the denominator, alright. and to make this insensitive to beta, what does that mean? It means that insensitive to transistor replacement, alright. It is transistor replacement which causes the maximum change in beta. So, if I wish to make I sub c independent of beta, what I should do is I should make Re much greater than Rb plus Re divided by beta, which means that Re should be, well, beta minus 1 Re. See, if I multiply beta Re and I bring Re from right to left, this should be much greater than Rb, alright. This is the condition for independence to beta, and you know beta is much greater than 1, therefore this condition approximates to Rb much less than beta times Re, because beta is much greater than 1. Therefore, one of the conditions in a stabilized biasing is that this design condition should always be fulfilled. Rb must be much less than beta Re. And in electrical engineering, much less than or much greater than always can safely be taken to be 1:10. And therefore, if you know beta, you know Re, what you choose Rb as minimum beta Re divided by 10. Which beta should you take? The nominal or the worst case or the worst minimum case or worst maximum case? Which? Minimum, alright, because you are taking much less than, and therefore Rb must be much less than beta min Re, which means that the lowest value of Rb that you can take is beta min Re is the lowest value or the highest value? Highest value. The highest value of Rb that you can take would be, well, let me put it here, Rb highest is equal to beta min Re divided by 10. This is a golden rule of thumb and must always be kept near the thumb, alright. It must always be remembered. This is one of the basic design conditions of a BJT biasing circuit. Let us look at the expression again to find out other parameters. Now suppose I satisfy this, condition, alright, then my expression will simplify to the following. It will simplify to VBB minus VBE plus beta plus 1 divided by beta we take as 1. So, I sub CBO times RB plus RE. Is that okay? If we compare the previous expression, beta plus 1 divided by beta we take as 1, and therefore ICBO RB plus RE, and in the denominator we shall have simply Re, because that beta term is negligible. Now, how do I reduce my dependence on ICBO? ICBO, as you know, doubles for every 10 degree centigrade rise in temperature. So, what I have to do is that this term ICBO RB plus Re must be made very small compared to VBB minus VBE. Now, who determines VBB? Obviously VCC, and therefore the higher the value of VCC, the better will be the stability. There is also a choice in ICBO. You see, for silicon transistors, ICBO is much smaller as compared to germanium transistors. For example, a typical silicon transistor, as I said, ICBO could be 10 nanoamperes, whereas for germanium transistor ICBO could be as large as 5 microamperes. So, microampere is in a relative terms is a small quantity, but relative to 10 nanoamperes, obviously 5 microampere is a large quantity. 5 times 10 to the minus 6 and 10 times 10 to the minus 9. And this is why silicon transistors are much more preferred than germanium transistors. This is one of the reasons that ICBO is much smaller. Okay. Now normally in a silicon transistor, if you choose your VBB properly, then this will be satisfied, alright. In any case, you must see that this inequality is satisfied. This is one of the inequalities. Finally, the devil is VBE, which decreases at the rate of 2.5 millivolt per degree C. How do you reduce the dependence on VBB? VBE, obviously what you should do is VBE should be much less compared to VBB. And how do you obtain this? VBB is VCC R1 by R1 plus R2. You must choose your R1, R2 and VCC such that this relation is satisfied. Okay. So these are the basic design parameters of a BJT. As you can see, as far as temperature is concerned, in this expression we have eliminated beta, alright. In this expression the temperature dependent quantities are two, one is VBE and the other is ICBO, and therefore if temperature changes from capital T to capital T plus delta T, alright, then what would be the corresponding change in I sub C? That is, what would be delta I sub C? Obviously delta I sub C shall be, VBB is independent of temperature, so minus delta VBE minus delta VBE plus delta ICBO times RB. I am intentionally ignoring RE because usually RB is one order higher than RE, that is approximately 10 times RE, and therefore I am ignoring that, this divided by RE. This is a simplified expression for calculating the temperature dependence of I sub C. For example, if you take a silicon transistor, then VBE is 0.7 volt and ICBO typically is 10 nanoamperes. For a germanium transistor, the corresponding figures are 0.3 volt and let us say 5 microampere. And suppose there is a 50 degrees centigrade rise of temperature. Suppose delta T is 50 degrees C. Then the question is, how much does I sub C change? Delta I sub C contains two quantities, one is delta VBE and one is delta ICBO. Due to 50 degrees centigrade rise in temperature, what will be the factor by which ICBO changes? 2 to the 5, that means 32, alright, and therefore the new ICBO shall be 32 times 10 nanoampere, 32 times 5, and delta ICBO should be 31 multiplied by these two quantities. Is that clear? Is that clear why 31? Yes. Okay. So if I take silicon, delta I sub C shall be equal to, let us take some specific values of RE, or let us take for the same design, the design that we had just, let us take 2 kilo, okay, 2K, and what did we take RB? 9K or 9K, alright. Then delta ICBO for silicon would be 332 times 10 minus 10, so 310 multiplied by 10 to the minus 9, then plus, now you see what happens, delta VBE actually decreases with rise of temperature. So what would be delta VBE? It would be, delta VBE is negative, but because of minus delta VBE it will be an addition, and delta VBE therefore shall be minus 2.5 millivolt multiplied by 50. which is equal to minus 0.125 volt. Is that correct? 125 millivolt, which is 0.125. So this would be 0.125. I must multiply by 10 to the 3. 10 to the 3. And this figure calculates out to 0.05 milliampere approximately. Do you understand this calculation? Okay. On the other hand, one can now say if it is germanium and you proceed with the same calculation, delta VB is the same. Isn't that right? Delta VB is the same. It is only delta ICBO, which now becomes how much? 31 times 5 microampere, which is 155 microampere. If you put that, delta I sub C calculates out to 0.75 milliampere, and you see the range of variation. Whereas this is only 0.05, germanium, same rise of temperature can cause a large change in I sub C, and this is the reason why silicon is always preferred, particularly where the device has to work under extreme temperature conditions. Alright. We can now summarize the methods, the procedure for BJT biasing. What are the steps? The steps are that the first thing is to do is to choose a cue point. How to choose a cue point we shall illustrate later, but first choose a cue point. What does this mean? It means choosing an I sub C, the collector current. It means choosing a V sub CE. Alright? And if you know the nominal beta, then obviously you know I sub B also. You know I sub B if you know beta. Alright? These two quantities are enough to specify a cue point. This is an additional information. That is, on the characteristics, which characteristic does the cue point lie on? You know that the characteristics are irregularly spaced parallel lines depending on the values of beta, depending on the values of I sub B. I sub B is the parameter, and therefore which I sub B line it lies on. This is an additional point. Next you have to determine, next you have to go to the emitter. You recall that the emitter has a resistance Re, and the current through this is I sub C plus I sub B. Alright. If Re is given, then of course you know what the drop across this is. If Re is not given, as is usually the case, you arbitrarily assume a value for VE. You assume a value for VE. Suppose your power supply that is given is, let's say, 12 volt. Then obviously Re cannot drop how much? It cannot drop 12 volts because there would be a VCE, there will be a drop in RC, and you don't want this drop to be large because you want a large swing in the output voltage. Typically this is chosen about 20 to 25%, rule of thumb again, there is nothing sacred about it. Alright, 20 to 25%, and one of the things that textbooks or manufacturers specify is arbitrarily choose VE equal to 3 volt. Now suppose this transistor is to go into a space instrumentation, into a space vehicle, where voltages are available are very small, maybe 1 volt is the total voltage available, then obviously this will not do. You will have to change the design appropriately, maybe 0.3 volt. But for normal operating conditions, 12 volt supply or 15 volt supply, you assume VE approximately as 3 volts. This must be done with care. If Re is given, you need not do this. But if Re is not given, you assume this to be 20 to 25% of the given power supply, and then you can calculate Re because you know IC plus IB. Alright. So the second step would be to determine an Re or V sub E. If Re is given, then you determine VE. If RE is not given, then you assume a VE and determine RE. All right. The next thing is select VCC, third step, VCC and R sub C. Select VCC and R sub C. Now, if VCC is given, if this is given, if the power supply is given, then what is R sub C? This will be VCC minus I sub C, well, I am sorry, R sub C would be VCC minus VE minus VCE, alright, because if you recall, the transistor is like this. This is VCC, VCC minus VCE minus VE divided by I sub C. So you can determine RC. On the other hand, if RC is known, it might be specified by the load. The load may be specified. Then if RC is known, then you calculate VCC. VCC would be I sub C RC plus VCE plus VE. Alright, this is the third step. Either you find RC or you find VCC. The next step is choose an RB. The next step is choose an RB, that is R capital B, which is the parallel combination of R1 and R2. Parallel combination of R1 and R2, which means R1 R2 divided by R1 plus R2. And I have already told you that this should be chosen as beta minimum times RE divided by 10. Alright, far less than or far greater than 1:10. So you choose an RB, alright, and once you have chosen an RB, why divided by 10? What I want is RB should be much less than beta RE. This is the rule of design, alright, much less than. Therefore, it must satisfy the expression even when beta is beta minimum, and much less than or much greater than in electrical engineering is what? 1:10 ratio. That's enough. This is why I divide by 10. You can divide by 20. There is nothing sacred about it. All right. This is a arbitrary figure, but divided by 10 is taken to be specifying much less than or much greater than. And the fifth step is after you choose this, you know R1, R2. You also know that VBB is equal to VCC R1 divided by R1 plus R2, and this would be equal to, if you recall, the Thevenin equivalent circuit at the base emitter junction. This is equal to I sub B RB this was the circuit. VBB is equal to IB RB plus VBE plus VE. All right. You know VE, you know VBE, you know IB, you know RB. You have chosen it. All right. And therefore, you know two things. One is R1 R2 divided by R1 plus R2, and the other thing that you know is R1 divided by R1 plus R2. From these two, then you find out R1 and R2, and these complete the design. We shall now have a break for 5 minutes and then continue with the design.